Hello, my name is Kushal Manjunatha and welcome to my presentation for SIT718 Assessment 2. In this assessment, I analyzed red wine quality using mathematical aggregation functions. The focus was on understanding the influence of selected chemical properties on wine quality scores and using models for accurate prediction. This method not only helps in analysis but offers interpretable insights for decision making in wine productions. Here I used a curated datasets of 460 red wine samples drawn from a larger dataset. Each sample includes several chemical attributes, but for this study I focused on five, like citric acid, chlorides, total sulfur dioxide, pH, and alcohol. The target variable is quality rated on a scale from 0 to 10. These variables are known to impact wine flavor, stability, and market value. To understand the underlying patterns, I visualized each variable using histograms and scatter plots. This revealed that chlorides and alcohol had a right skew distribution, suggesting the need for normalization. pH and citric acid had a moderate variance. Understanding the distribution is critical before fitting any models to avoid biases and improve interpretability. So this is the histograms of chemical attributes I have focused on. Like here is the histogram for citric acid, chlorides, sulfur dioxide, pH, alcohol, and quality. And this is the scatter plots for the chemical attributes used. Among all features, I selected four key independent variables that are citric acid, chlorides, pH, and alcohol. These were chosen based on their range, correlation to the output variable, and relevance in the winemaking process. For example, citric acid adds freshness to wine, while high chlorides could degrade quality, and alcohol is directly linked to perceived strength and taste. To prepare data for modeling, I applied mathematical transformations. Citric acid and chlorides were square rooted to reduce skewness, pH was raised to 1.5 and alcohol to 1.2 to normalize their effects. The target variable quality remained untransformed for interpretability. Following this, all values were normalized using min-max scaling to keep them within a 0 to 1 range. This step ensures comparativity across variables. I used multiple aggregation functions, particularly the weighted arithmetic mean, two weighted power means with power 0.5 and 2, and the ordered weighted average or OWA. These models differ in how they assign importance to variable and how they combine inputs. The goal was to find a function that fits the data well and provides interpretable weights for each feature. Here you can see a comparison between models using four key metrics: root mean square error, average absolute error, and two correlation coefficients. The OWA model produced the lowest RMSE at 0.17 and decent correlations, suggesting high accuracy and consistency. WPM with P is equals to 0.5 performed well too, but with slightly higher error. This slide shows the weights each model assigned to the variables. In WPM, citric acid had the highest weight while chlorides had 0, suggesting low importance. In contrast, OWA gave most weight, about 58% to alcohol, indicating it's the dominant factor in predicting quality. Orness, a measure of optimism in aggregation, was 0.779 for OWA, indicating preference towards higher input values. From these weights, we conclude that alcohol significantly impacts wine quality, which aligns with domain knowledge. Chlorides contribute moderately, and citric acid plays a subtle role. This kind of insight is valuable in tuning production process. Although WPM offers simple interpretability, the OWA model was the best in terms of performance. It minimized both RMSE and absolute error while maintaining good correlation, making it the most suitable model for prediction in this context. A new input sample was tested with transformed values for citric acid, chlorides, pH, and alcohol. After normalization, the model predicted a quality score of 4.23. This was achieved using WPM with weight P is equals to 2, and it's important to note that predictions are done in the normalized space and then scaled back for real-world interpretability. Here the prediction is reasonable based on the input, where alcohol brings up the score and chlorides and sulfur dioxide slightly reduce it. To achieve high quality, our analysis recommends low chloride levels which prevent saltiness, higher alcohol levels which enhance body, and a balanced pH near 3.3 to 3.5 for optimal taste and preservation. Citric acid should be moderate, not too high to avoid soreness. These models are powerful tools in production and quality control. The aggregation framework offers both predictive capabilities and interpretable insights. By understanding which factors are more influential, producers can make data-driven decisions. There are several limitations to keep in mind. First, linear assumptions may oversimplify relationships. Also, choice of transformation affects model output, and the data is specific to one region, limiting generalization. Although the data is anonymous, future applications involving consumer feedback or preferences must comply with privacy laws like GDPR. It is vital to anonymize, seek consent, and avoid using sensitive information inappropriately. To conclude, using aggregation functions enabled effective analysis of wine quality. OWA turned out to be the best performer. These results can guide producers in optimizing quality based on measurable properties like alcohol and chlorides. This methodology also shows potential for broader applications beyond winemaking. Thank you.